Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 29, The Geology of the Moon. In our last lecture, we looked at impact cratering, both on the Moon and on the Earth. In this lecture, we're going to take a more detailed look at the history of the surface of the Moon. And in particular, we will start with where we left off in the last lecture, and that is that the different parts of the surface of the Moon have different ages. This is yet another Lick Observatory photograph of the near side of the Moon, and it very clearly shows the two types of terrain. The highlands down here, which are covered in craters, and the smooth maria, which are not. The maria, or the seas on the Moon, are lava flows on the surface of the Moon, and they don't have nearly as many craters because they haven't been exposed to space for as long. The highlands down here are completely covered in craters, and that's because they've been exposed to space for a long time. There's been a long period of time to build up craters on top of craters. So that means the highlands down here are the oldest part of the Moon, and the maria here are the youngest parts of the Moon. These parts have been exposed to space for a long time. These parts have been exposed for less time. So, like I said in the last lecture, just with a pair of binoculars or a telescope, looking at the Moon, you can not only see the highlands and the maria, but you can make out this basic geologic fact that they have different ages, and through your binoculars you can actually tell which parts of the Moon are younger and which parts of the Moon are older. But now let's look in a little bit more detail. And in order to understand the history of the near side of the Moon, let's take a technique out of Earth geology and apply it to the surface of the Moon. And we're going to do what the famous lunar geologist Eugene Shoemaker did back in the 1950s and 1960s. So let's start with the Earth. You're probably familiar from prior education that the Earth history is broken down into eras and eons and periods. And so you're probably familiar with things like the Precambrian, or for those of you that are dinosaur fans, the Triassic, the Jurassic, the Cretaceous right there, the Carboniferous, the Devonian, the Silurian. There are all these different periods in the history of the surface of the Earth. So over here, let's start here on the left. This is the full history of the Earth over the last 4.6 billion years. So here is the formation of the Earth. Here is today. The first thing to know is that most of the history of the Earth is called the Precambrian. And the reason that most of the history of the Earth is crammed into the Precambrian is that most of the creatures that lived, most of the life that lived during the Precambrian, did not leave behind fossils. It turns out that most of these periods are defined by the fossils that were left behind. See, what would happen is geologists would go out and they would see in a certain area fossils in the rocks. And they would notice that some rocks were on top of other rocks, on top of other rocks, so they could look at the layers and they could measure the fossils that they saw in those layers. But then they could go someplace else and they could see the same exact layers with the same exact fossils. And sometimes they could go hundreds or thousands of miles away and see the same layers with the same fossils. So they realized that when something was going on the Earth, it was happening over a widespread area, and that event, or whatever it was preserved in the fossil record. And so as we look at these periods, we can see the Carboniferous, for example, a time when there were huge forests on the surface of the Earth. This is where much of our coal comes from today. As these trees fell and were converted to carbon over time, this is the era of coal. And then, of course, the era of the dinosaurs, beginning about 250 million years ago and ending 65 million years ago. We call that era the Mesozoic, and it's divided into three periods: the Triassic, the Jurassic, and the Cretaceous. These periods are defined by the fossils that we find in the ground. So all of this time is based up here. It starts with the Cambrian explosion. The Cambrian explosion, you might remember from our tour of the universe in the second lecture. That was that event in which there was an amazing diversification of all the life on Earth. And that marks the beginning here of the Cambrian period on Earth. And before that, we get the Precambrian, when there really wasn't much life on Earth, and there wasn't life, and maybe that's not the right way to put it, there was not life on Earth that left fossils. There was lots of single-celled organisms, even multi-celled organisms, even soft organisms, but they didn't leave behind fossils. But starting in the Cambrian, we now see lots of complex animals that leave behind shells, that leave behind skeletons, that leave behind fossils. And as they evolve and change over time, new periods were defined. And of course, the most recent times on Earth are defined up here at the top in the Tertiary. And we can see those as the Paleocene, for example, coming all the way up to the Holocene, which is the present epoch that we have today. So scientists laid out the history of the Earth by looking at these layers of fossils. Now, I've mentioned a primary law in the study of geology, which is the law of superposition. Now, remember that laws are not absolute, that laws describe a relationship. And in this case, they describe the relationship between the older and the younger rocks. In most cases, the vast, vast majority of cases on Earth, when you see sedimentary rocks like this that are laid down in layers, the older rocks are on the bottom and the younger rocks are on the top. And that's because of how sediments get laid down. As sediments wash out into the ocean, they get laid one on top of the other on top of the other. And the younger ones are on top and the older stuff is on the bottom. It doesn't happen in geology that you suddenly split open a whole bunch of layers and insert a whole bunch of rocks. There's not a good geologic process for doing that over widespread areas. Now, sometimes there can be a violent event on Earth that takes some of these layers and flips them over. Could be an impact crater. Could be a fault where these blocks fault against one another. But those are typically localized, and over wide areas, it's generally true that the rocks on the bottom are older than the rocks on the top. And this is the law of superposition, and it's also called stratigraphy, or the study of layers in rocks. So by studying these layers, we can lay out the geologic history of the Earth. It turns out these layers exist on other bodies as well. Those layers exist on the moon. Those layers, different layers, I should say, exist on the moon, and different layers exist on Mars, but layers exist. We'll come back to the moon. I'm sure looking at the moon right now, as you examine it closely, you can't really identify any layers, and I'll help you find some layers here in a little while. But let's talk a little bit about how we're using layers like this on Mars. The primary goal for the Curiosity rover sitting on the surface of Mars is to find evidence for past water on Mars and to map out the geologic history of the planet. And the place that it has landed is a giant crater called Gale Crater. Billions of years ago, an impactor struck the surface of Mars and blew a giant crater. And then, over the subsequent billions of years after that, sediment layers were laid down on the surface of Mars. Some thin sediments, some thick sediments, but they were laid down with the oldest layers on the bottom and the youngest layers on the top. And then, in more recent times, the winds on Mars changed. And as those winds changed, they eroded all those layers. And what we have now is a giant crater. And sitting in the bottom of the crater is a mountain of rocks. But from orbit, it was clear that that mountain consists of many different layers. And each one of those layers records millions of years of history of geology on the surface of Mars. So the goal of the Curiosity rover was to land at the base of this mountain and drive up the side of the mountain and sample these different layers to figure out what was going on Mars. Now, from other evidence, we knew that when there was water on Mars was the early history of Mars, billions of years ago. So it turns out the oldest layers are the most interesting ones. So Curiosity is not likely to climb all the way to the top of the mountain. It's going to focus most of its effort down here on the lower layers, which are the older layers, which were the layers where we are most likely to find evidence of liquid water in the past. And I can tell you that that is exactly what Curiosity has found. Lots of evidence for liquid water billions of years ago. To take it from abstract to show you what Curiosity sees, this is one of the early photographs taken by the Curiosity rover not long after landing, looking at the flank of Sharp Mountain. So Mount Sharp is the mountain that sits in the middle of Gale Crater, and that is the mountain whose flanks Curiosity will be driving up has been driving up for the last 8 years and will be driving up for the foreseeable future. Now, if we take a close-up look at those distant mountains, now we can see the individual layers. Geologists absolutely love seeing layers like this because each one of these layers is laying out millions of years of history on the surface of Mars. And all the layers taken together lay out billions of years of history on the surface of Mars. So with this one mountain driving up the side of the mountain, measuring what's going on in each layer, we can lay out a geologic history of Mars. And that is the primary research goal of the Curiosity rover operating on Mars today. We can do the same thing for the moon. The famous lunar geologist Eugene Shoemaker was studying the moon back in the 1950s, and he wrote one of the most important papers about the moon, where he laid out the geologic history of the near side of the moon by looking at the various layers that you can see. And the part of the moon that he used here was the southern half of Mare Imbrium, the Sea of Showers right here. So Mare Imbrium is a round sea on the moon, and it is 712 miles in diameter. And the rim of Mare Imbrium right there is marked by the Apennine Mountains right here, the Alps Mountains right there, and it is filled with lava that flowed in. As you can imagine, this round circular feature, you will notice that many of the seas on the moon are round in feature. The roundness comes from the fact that these are impact basins. Mare Imbrium is an ancient old impact basin. The mountains that you see are actually the rim of the crater, and the crater has since been filled in by lava. And so that's why it looks very flat and smooth, because the lava flowed up and filled in that giant crater. The same is true here with the Sea of Serenity, Mare Serenitatis. We can see the mountains that mark the rim of the crater, and we can see the lava that flowed in. The Sea of Tranquility, the Sea of Fertility, and the Sea of Crises are all the same as well. Most of these maria are round because the lava flowed into the low-lying areas of these deep basins, and the lava flowed from the bottom up. We'll talk more about that later on. But what we're going to do is we're going to study the bottom half of Mare Imbrium right here. So let me take this and blow it up. So we're going to cut it off right about here. So we're going to cut it off right about here, and we're going to come down to about here. So let's blow up this part of the image. So there is the blow up of that part of the image. So let's talk about what we've got here. We've got this mountain range right here. So we've got this mountain range. That's the Apennine Mountains, and we're going to designate that with the letters AP. So there are the Apennine Mountains. And then we've got the crater Copernicus right here. It's about 60 miles across in diameter right there from rim to rim. So about 100 kilometers across. So that's the great crater Copernicus. There's the crater Eratosthenes. We saw that in the last lecture. A beautiful example of a complex crater with a central mountain, terraced rims, an ejecta blanket around it, secondary craters. We've got the crater Archimedes right here. So that's the crater Archimedes. We've got another crater Autolycus right here. And then we've got the lava that flowed into the giant basin here, the dark-colored basaltic lava that's almost black in color, flowed all the way up to the mountains here, covers the region down here. And we're going to mark that with the letters IM. When you look at this image, layers are starting to appear. And what I mean by layers is that you can see that some things are sitting on top of other things. Now, it may not be completely obvious, but if you look carefully, you'll notice that some things are clearly on top of other things. If something is on top of something else, that means it's younger. If it's below something else, it means it's older. And from the layers that we can see here, we can actually lay out the geology of this part of the moon. So let us start with the great crater Copernicus down here. Eratosthenes, So there's Copernicus seen up close. Copernicus is a complex crater. We see lots of secondary craters, lots of material that was thrown out of Copernicus right there. Here's the crater Eratosthenes right there. So there is Eratosthenes. There are the Apennine Mountains. You can clearly see the ejecta blanket around Eratosthenes. And then there is the crater Archimedes right there. So that is Archimedes. What I want you to do is I want you to look at these layers, and I want you to go to Learning Catalytics right now, and I want you to answer this question. Which of these features is the youngest? Which one is the youngest? Is it the Apennine Mountains? Is it the crater Copernicus? Is it the Mare Imbrium lava flows? Is it the crater Eratosthenes or the crater Autolycus? Go ahead, take a minute or two. You'll definitely want to pause the video on this one. Stare at this image for a while. See if you can find the layers. See if you can work out what is on top of everything else. And find the youngest thing. The youngest thing will be on top of everything else. So go ahead and do that. Take a minute to do that. Okay. What did you find when you looked and tried to find the layer that was on top? So, one of these things I think is clearly on top of everything else, and it's probably the most obvious one. But let's go over some of these. So let's start with the crater Copernicus right here. So the crater Copernicus is a giant impact crater on the surface of the moon. There's an ejecta blanket around it, but most importantly, we see the rays coming out of Copernicus. Rays are material that came out of the crater and splashed off at long distances. They're very often associated with secondary craters. That is, this is material that came out of Copernicus and splashed across the surface. So what you'll notice about Copernicus is that the rays from Copernicus are sitting on top of the lava flows. That is, if you look at the lava flows here, if the lava had flowed on top of the rays, we wouldn't be able to see the rays. The lava would have buried the rays. So right away, we can say that Copernicus is younger than the lava flows because the lava flows would have covered up all these rays if they had happened after. I think it's also obvious looking at the Apennine Mountains right here that Copernicus has clearly draped its material across the Apennine Mountains. That is, the mountains existed first, Copernicus happened second, and the material splashed down on top of the mountains. We see no evidence that the mountains impeded the flow of material, and we see that the mountains here seem to be covered in the ejecta from Copernicus. Well, what about Eratosthenes over here? Did Eratosthenes come before or after Copernicus? That's a harder one to decide, but here's the most convincing evidence. The most convincing evidence comes from secondary craters from the crater Copernicus. If we look at Eratosthenes right here, we see the crater Eratosthenes. We see the ejecta blanket that was blown out of Eratosthenes. And sitting on that ejecta blanket, we see secondary craters. But this particular set of secondary craters are in the shape of a V, and they point right back at Copernicus. What that means is that these craters were created on top of the ejecta, which means that Copernicus had to come after Eratosthenes. Eratosthenes was here first, and those craters landed on top of Copernicus. The craters from Copernicus landed on top of Eratosthenes. So Copernicus is the younger of the two. I think another really nice example of that is if we look at the ejecta from Copernicus here, you will notice that there's a shadow behind Eratosthenes right here. The ejecta from Copernicus flowed across the surface, but because of the raised rim of Eratosthenes, there's a protected or shadowed area back here. And that meant that Eratosthenes existed before Copernicus. So I would argue that the youngest thing in this photograph is the crater Copernicus. So if we were to draw a diagram showing the layers, you should draw the oldest layers on the bottom and the youngest layers on the top. And what I want you to do now is on a piece of paper, draw the word oldest at the bottom of the paper, youngest at the top of the paper, and write C for Copernicus at the top of the paper. The next thing I want you to do is answer the question, which of these things is the oldest? So go into learning catalytics now and pick the one that is the oldest. The oldest one sits below everything else. So go ahead and take a minute and solve that puzzle. Which of those units is the oldest? Okay, what did you come up with for the oldest unit? This one's a little bit tougher, but this one you have to think a little bit more about what each of these things represent. So we've talked already about these impact craters. These impact craters are where various comets and asteroids struck the moon. The lava flow, we haven't really talked about where that lava came from. We'll talk about that later on. But there's this lava flow on the moon, and then there's this mountain range. Which one is the oldest? Well, clearly Copernicus sits on top of the mountains. So the mountains are older than Copernicus. I would argue from this photograph right here that it's pretty clear that the ejecta from Eratosthenes has draped over the mountains. You'll notice how crisp and clear the mountains are here and how fuzzy they get right there. That's because they are draped in ejecta from Eratosthenes. So Eratosthenes is younger than the mountains. So both Copernicus and Eratosthenes are younger than the mountains. What about this lava flow here? Are the mountains on top of the lava? It looks like it right here, but here's the thing. Remember that lava flows. And what was really going on here was the lava flowed, and it flowed right up to, but stopped when it reached the taller mountains. We call this process embaying. The lava embayed the taller mountains right here. Probably the most convincing evidence for why the mountains are the oldest is to think about what the origin of those mountains are. Where did they come from? Remember, those mountains are the rim of a giant crater. And that crater is Mare Imbrium, or I should say, I'm sorry, it's not Mare Imbrium, it's the Imbrium Basin. That the rim of that crater is the giant Imbrium Basin under there. Here's the thing. When the Imbrium Basin was made, it would have destroyed everything else in the photograph, right? When that giant body struck the moon and blew this huge crater, all of these craters that are inside it would have been destroyed. They all had to come later. The lava would have been destroyed. It had to come later. Even these craters just outside the rim would have been destroyed. They had to come later. The thing in this picture that has to be the oldest is the Apennine Mountains, because the Apennine Mountains sit below everything else. When they were made as the rim of that giant crater, and that impact would have destroyed Archimedes and Autolycus and the lava flow, and it would have destroyed Copernicus and Eratosthenes. So the Apennine Mountains have to be the oldest. All right. Now I want you to answer which is the second oldest. Of all the units that you can see here, which one is the oldest? On your piece of paper with Copernicus at the top, I want you to write the Apennine Mountains at the bottom. What is the second oldest unit? What came after the Apennine Mountains, but before anything else? All right, were you able to figure this one out? It's a hard one. It's not easy to do because we're faced with Eratosthenes, we're faced with Archimedes, we're faced with Autolycus right here, and we're faced with this lava flow. It looks to me, we already have identified that Copernicus is sitting on top of the lava flow. It also looks to me like Eratosthenes is sitting on top of the lava flow. It's not quite so obvious here, but when we look back at that image of Eratosthenes, here's the lava out here. Here's the lava in here, and there are clearly secondary craters from Eratosthenes that are on top of the lava flow. So Eratosthenes is definitely younger than the lava flow. We can also see Autolycus over here, and we can see the crater, but we can see the ejecta blanket around Autolycus. So it's clear that Autolycus came after the lava because the ejecta blanket for Autolycus is sitting on top of the lava. So now you're probably leaning towards the lava, but here's the problem. Look at Archimedes. There's something wrong with Archimedes. There's something missing from Archimedes. What is it? Well, the thing that's missing is the ejecta blanket. A crater the size of Archimedes should have an enormous ejecta blanket around it. Where is that ejecta blanket? The answer is, it's under the lava. Archimedes was created first, and then the lava flowed second. And the lava completely covered the ejecta blanket from Archimedes. Not only that, but the lava flowed up inside and filled inside Archimedes. So now that when we look at Archimedes, whoops, where's my close-up picture of Archimedes? There it is. So now when we look at Archimedes today, we see the floor, the center of Archimedes is covered in this smooth lava. And the ejecta blanket and everything surrounding all the secondary craters from Archimedes have all disappeared. They're all gone, because they're covered by the lava. So the answer to this, what is the second oldest unit? The second oldest unit on here is Archimedes, the crater Archimedes. All right, now I want you to figure out the third oldest unit. So right above, right on the bottom of your page, you've got the Apennine Mountains written. Right above it, you've got the crater Archimedes. What came next? What is the third oldest unit on here? So go to Learning Catalytics and answer this question. What is the third oldest unit? All right, what did you get this time when you were looking at this for the third oldest unit? I think this one you're probably getting a little bit easier now, because we said in our last bit that Autolycus right here is clearly on top of the lava, and Eratosthenes is on top of the lava. So if Archimedes is below the lava and Eratosthenes and Autolycus are on top of the lava, then the lava flow had to come next. So the order is, from the bottom up, is the Apennine Mountains, Archimedes, the lava flow, and then at the very top is Copernicus. And what we next need to decide is Eratosthenes and Autolycus. And here's the problem. Autolycus and Eratosthenes are far enough apart that we can't actually determine which one came first and which one came second. It's also complicated by the fact that Eratosthenes was damaged by all the ejecta from Copernicus right here. So sometimes we can use the freshness of the crater, how fresh it looks. You'll notice that Copernicus, with all this fresh ejecta on the surface, looks like a young, fresh crater. Over time, this ejecta darkens and disappears. But when it's young and fresh like Copernicus is, that ejecta is quite bright. Over time, so Autolycus, we can still see some of its ejecta blanket here. Eratosthenes, it's hard to tell because there is so much ejecta from Copernicus around it. So what I want you to do is you have the Apennines at the bottom. You have Archimedes next. You have the lava flow, the Imbrium lava flow next. You can put Eratosthenes and Autolycus together because we really can't tell which one came next. But we do know that Copernicus is younger than both of them. And so Copernicus goes on the top. So now we have laid out the geologic history of this area. So before we tell the story of what happened here, I want you to take a guess at this. Did the Mare Imbrium lava quickly fill the Imbrium impact basin? That is, did you have this giant impact blows a basin and the lava fills in right away? Or did the lava come much later? And looking at the picture, you can actually tell that, but it's a subtle tell. So mostly I want you to try and guess the answer here. Yes, the lava filled the basin almost immediately, or no, sometime past, hundreds, tens, or hundreds of millions of years. So go ahead and answer that in Learning Catalytics. All right, what do you think on this one? This one was a lot harder, but the key to understanding this one is the crater Archimedes right here. And the key to understanding it is Archimedes, because remember, Archimedes came after the crater, after the basin, the Imbrium basin was created, when the Apennine Mountains were pushed up. Came after the basin creation, but before the lava flows. The thing is, Archimedes is a big crater. And big craters like this don't happen on the moon every year. They don't happen on the moon every hundreds of years. Craters like this happen on the moon once every tens of millions or hundreds of millions of years. And that means that a long period of time had to go by before the lava buried Archimedes. The basin and the lava are separate from one another. And that's a really important thing to understand. The basin, which is the giant crater, is separate from the lava. The lava flowed up from underneath. And by the way, I should mention, now is a good time to mention, well, I'll mention it here in this next slide. So let's tell the story of what happened to this part of the moon. Here's what happened. The moon formed 4.5 billion years ago. A giant crater, a giant impactor about 70 miles across, impacted the surface of the moon, and it blew a huge basin in the moon that we now know as the Imbrium Basin. Then radioactive materials in the crust of the moon. Remember that one of the things responsible for the heating of the center of the Earth is radioactive materials. The same thing is true with the moon. Radioactive materials in the crust and underneath the surface of the moon, as they decayed and they released their heat had no place to go because they were buried deep underground. So deep underground the surface of the moon, it got hotter and hotter until some of the rocks melted. Those molten rocks worked their way to the surface and started creating the lava flows on the surface. But here's the thing. A crater, Archimedes, was created on the surface of this basin before the lava flowed. And as I said, these craters don't happen very often, so it's likely that the lava didn't flow into the basin until many, many millions of years, tens or hundreds of millions of years after the basin was created. The basin is made, it solidifies, and then later the lava flowed up. And it turns out the lava fills in these basins simply because the lava is coming from underground, and that lava fills in the low-lying areas first. And because those basins are deeper than the rest of the surface of the moon, it's natural that they will fill up first. Now there are many repeated lava flows, lava flow after lava flow after lava flow. The Maria, the seas on the moon, were not one giant lava flow. They were actually many hundreds of different lava flows. And you can actually see that in this photograph. You'll notice that the Maria over here are lighter in color, and the Maria here are darker in color. And there's a darker patch here and a darker patch here. There's darker patches elsewhere. You can see here that there's lighter colored patches and darker colored patches. The Maria, when they erupted on the surface of the moon, erupted from many different small volcanoes and fissures in the surface of the moon. And as this lava flowed up, it wasn't one giant lava flow. It was many small ones here and there over time. So the lava flows in and it fills in these low-lying basins, and that's where we get the seas on the moon. Now that the lava has flowed in sometime later, other craters hit the moon. Autolycus hits the moon. Eratosthenes hits the moon. And then recently Copernicus hits the moon. That is the geology of this part of the moon. The order, again, is that a giant thing creates the Imbrium Basin. And then another crater hits, another asteroid hits, and it makes Archimedes. And then sometime tens of millions of years after the initial creation of this giant basin, the lava flows in and fills it in. And after that, we have Autolycus and Eratosthenes hitting the moon, and then most recently we have Copernicus. Now, Eugene Shoemaker picked this part of the moon for a good reason. The Imbrium Impact Basin was a giant impact. As we'll see here in a second, it affected the rest of the near side of the moon. But this part of the moon was so important in determining how old these things are. Well, let me stop for a second and say this. When I tell you that something is older than something else, the Apennine Mountains are older than Archimedes, which is older than the lava flow, you'll notice I didn't tell you how much older. All we can say is that one is older than the other. In order to determine exactly how old they are, we have to go to the moon and get samples and bring them back. And that was the primary goal of the Apollo missions to the moon. The Apollo missions to the moon were designed to go to the moon and bring samples back to Earth. And the radioactive elements in those samples could be used to determine the ages of those rocks. The single most important geologic event on the near side of the moon was the creation of the Imbrium Basin, because as we'll see in a minute, the Imbrium Basin affected lots of other areas on the near side of the moon. And so geologists very much wanted to know how old the Imbrium Basin was. It was so important in determining the age of the Imbrium Basin that 2 separate Apollo missions were dedicated to just that topic. We only landed on the surface of the moon 6 times, but 1/3 of the missions, 2 of them, were dedicated to the Imbrium Basin. The first one was the Apollo 14 mission, and they landed here on the surface of the moon. And down here, this is material that it's called the Frau Mora Formation. This is material that was molten, and when the Imbrium Basin was created, this molten material was splashed out on the surface of the moon. And when it was splashed out on the surface of the moon, it was molten and then froze. And Apollo 14 landed on this material because, based on its geology and its location, and the fact that it has lots and lots of striations, which indicate that it came out of the Imbrium Basin, this was material that was melted in the impact, was splashed out, and then immediately froze after the impact. Its age, how old it is exactly the age of the impact. And so that is why a whole Apollo mission, Apollo 14, was dedicated to landing here, sampling this molten material so that it could tell us how old the Imbrium Basin is. But that wasn't enough for geologists. The second mission that was dedicated to this was Apollo 15. Apollo 15 set down right here at the base of the Apennine Mountains. And they set down here at the base of the Apennine Mountains because Apollo 15, this is an image from Apollo 15. That's Mount Hadley in the background. That is one of the Apennine Mountains, rising about 15,000 feet above the surface of the moon. Apollo 15 was the first mission with a rover. With the rover, they could drive up onto the flank of this mountain and sample the mountains to determine how old these materials were. These mountains are believed to be derived from material that used to be below the surface that was pushed up in the formation of this basin. And in that process, by driving up onto the flanks of the mountains and sampling this material, we might sample stuff that was deep down underground and very, very old. But at the same time, other rocks would have been created at the same time the mountains were created. And by driving up into the mountain and collecting rocks on the plain, the astronauts could measure how old the basin itself was. And then finally, there were some volcanic features in this area. There's an ancient lava flow, a rill, that flows through here, a lava tube, a collapsed lava tube that they were able to investigate as well. So the Apollo 15 mission, I would argue, was one of the most important, if not the most important scientifically, of the missions that landed on the surface of the moon, because it told us so much about the geology of the moon. Now, why was the Imbrium Basin so important? Well, let's take a look at this part of the moon down here. This part of the moon is clearly separated from the Imbrium Basin. So first we're going to look at this square right here, and we're going to look at just a topographic map of that part of the moon. And if you look at that topographic map, so here it is, this big topographic map, the first thing you'll notice is that it looks like somebody scratched this part of the moon. Look at it. You can see all these scratches running from upper left to lower right. What made all those scratches? It was ejecta from the Imbrium Basin. Even though that square is down here, so for example, you see this big round crater right here with the two below it. That's this big round crater right here, Ptolemaeus, with Alphonsus and Albertinius, Albertigenius right here. You see these giant three craters right here on the moon. You'll notice how scratched up they are. What these scratches mean is that these craters existed before the Imbrium Basin. Look at Ptolemaeus right here. Look at its rim. It's all scratched up. And by the way, Claudius Ptolemaeus, of course, is Ptolemy. This crater is named for Ptolemy, the astronomer that we studied in one of our earlier lectures. You'll notice how scratched up this rim is right here. That means that the crater Ptolemaeus existed before the Imbrium Basin. Even though we can't see the basin in this picture here, we can tell where it was because all these scratches point back towards it. And the rim of Ptolemaeus was damaged and broken by ejecta from the Imbrium Basin that came crashing across this part of the surface of the moon and cut and broke and damaged the rim of Ptolemaeus. But there are also craters in this area that are young and fresh and that clearly weren't damaged. Let's take a look at this region right here. So this is Halley, crater Halley on the surface of the moon, named, of course, after the astronomer of Halley's Comet. Let's look at a photograph of this part of the moon and see what we see. So in this part of the moon, we see right here, this crater Halley. You'll notice that its rim is clearly damaged by a long streak. and that long streak points back to the center of the Imbrium Basin. Clearly, Halley existed before the Imbrium Basin. It's older than the Imbrium Basin, because when the Imbrium Basin was made and material splashed across this part of the moon, it damaged the rim of the crater. But now look at this crater right here. This crater is young and fresh, and you look at how sharp and well-defined its rim is. In fact, this crater is sitting on top of scratches that were made in the Imbrium Basin. Because this crater is so young and fresh, it is clearly younger than the Imbrium Basin. So one of the reasons that Eugene Shoemaker focused so much on the Imbrium Basin and laying out the geologic history of the moon is that lots of things that are thousands of miles away from the Imbrium Basin, you can actually determine whether they came before or after the basin based on whether they are damaged and scratched by the material ejected out of the basin or whether they sit on top of that damage. Okay, that is the geologic history of the surface of the moon. The last topic I want to cover is, where did the moon come from? The best model we have for the origin of the moon right now is that the moon was created when a Mars-sized body struck the Earth right at the very beginning of the solar system, just after the formation of the Earth. So at this point in time, the Earth had differentiated. The heavy materials had sunk to the middle. The lighter materials had floated to the top. The same was true of this Mars-sized body. The heavy materials sank to the middle, and the lighter materials floated to the top. And what happened was this Mars-sized body struck the Earth a glancing blow. And as it struck the Earth a glancing blow, the outer layer of the Mars-sized body and the outer layer of the Earth were blown off into space, and they eventually regathered together. Gravity pulled them together to form the moon. So let's look at what happens here. The Mars-sized body strikes the Earth. The heavy, dense core of that Mars-sized body crashes down to the Earth and becomes part of the Earth's core. The outer layers of the Mars-sized body and the outer layers of the Earth are blown off into space, and they form this disk of debris, this disk of debris around the Earth. And that disk of debris, gravity eventually pulls it back together, and it forms the moon. And that answers an interesting question about our moon. When geologists and astronomers were considering the origin of our moon, one of the confusing things about our moon is it is a body big enough that it should have an iron-nickel core. But our moon does not have an iron-nickel core. Why not? Where is it? The answer is it was lost in the collision with the Earth. When that Mars-sized body struck the Earth, the iron-nickel core from the moon was incorporated in our core. The moon is made of the lower density rocks from the original surface of the Earth and the original surface of that Mars-sized body that were blown out into space. Another interesting thing about the moon is it's enriched in refractory elements, those elements that have very high boiling points. And it is also very deficient in volatile elements. Those are elements that have very low boiling points. What that indicates is that the surface of the moon, or I shouldn't say the surface, but the materials that make up the moon at one point in the past were heated to tremendous temperatures. That heating came about in this collision. When the Mars-sized object struck the Earth, that material in the collision was heated to such high temperatures that all the volatiles, like water, were baked out of the rocks and were blown away by the solar wind. So that when the moon reforms, because of being heated to such high temperatures, it lost all those things, all those volatile materials that had very low boiling points. That was one of the main results that came out of the Apollo missions to the moon. Was the Apollo missions to the moon showed that the moon rocks were, by Earth standards, very, very dry. That there was very little, there's some, but very little water in the moon rocks compared to Earth rocks. And that at some point in the past, they had been heated to very high temperatures. So now that we've told the story, and now that we know now that we've told the story, and now that we've brought samples back from the moon, let's talk about the formation history of the moon. So about 4.5 billion years ago, within 100 million years of when the sun and the planets in our solar system formed, the Mars-sized body strikes the Earth and the moon accretes in orbit around the Earth. Early in the solar system, the moon was very, very close to the Earth. And over time, the tidal forces have moved the moon farther away. But the moon once probably orbited extremely close to the Earth. After that, there was lots of there was differentiation. That is, the heavy things sank to the middle, lighter things floated to the top. But about 4.2 to 3.9 billion years ago, there were 30 giant basins created on the moon, 30 giant impacts. And in here, we also have the South Pole Aitken Basin. There were some other basins formed, but here's the big one. 3.84 billion years ago, the Imbrium Basin impact happens. That is, the Imbrium Basin was created on the moon 3.84 billion years ago. By the way, the Oriental Basin was the last large basin made on the moon, and it was about 3.8 billion years ago. From 3.8 billion years ago to about 3.2 billion years ago, that's when most of the lava flowed on the surface of the moon. So the lava flowed for 600 million years. It wasn't just one giant lava event. It was many thousands of lava flows over 600 million years that filled in those basins to make the Maria that we see today. Now, the lava flows mostly stopped by about 3.2 billion years ago. Some of them continued, but not nearly as voluminous as they did in the early history of the moon. So from 3.2 to 1.1 billion years ago, it's mostly a little bit of mare volcanism, a little bit of lava flows, but mostly just impact cratering, mostly just impacts hitting the surface of the moon. About 810 million years ago, Copernicus strikes the surface of the moon, and 110 million years ago, Tycho impacts the surface of the moon. Let me go back to this picture of the moon for a second, because I think that is absolutely fascinating. Look at this. Copernicus is one of the youngest, freshest craters on the moon, and it is 810 million years old. When Copernicus was made, there were just single-celled organisms on the Earth. There were no animals. It was still 300 million years before the Cambrian explosion, almost 300 million years before the Cambrian explosion. One of the youngest, freshest craters on the surface of the moon is ancient by Earth standards. And probably the youngest, freshest large crater on the moon is Tycho down here. And Tycho, it's 110 million years old. It was made at the height of the dinosaurs. And look at these lava flows, the lava flows. So the Imbrium Basin here is ancient, 3.8 billion years ago. But most of these lavas flowed from 3.8 to 3.2 billion years ago. The youngest of those lavas are 3.2 billion years old. That is older than the vast majority of rocks on the surface of the Earth. But most importantly, look at this. Those lavas are 3 billion years old, and they have hardly any craters on them. And the southern part of the moon, which is only a little bit older, has lots and lots of craters. This is a great indication that the early solar system was extremely violent. Right? The moon forms 4.5 billion years ago. These lavas flow 3.8 to 3.2 billion years ago. And since those lavas flowed, hardly anything has hit the moon in the last 3.8 billion years. All the major cratering on the moon was between 4.5 and 3.8 billion years ago. And we call that period of time the late heavy bombardment. This is when our solar system was clearing itself out. When you look at this heavily cratered portion of the moon down here, when you look at the heavily cratered far side of the moon, what you're looking at is the end of the formation of our solar system. That last period of time when all the giant planetesimals were being cleared out, when they were crashing into the planets, when they were being accreted onto the planets. And after that, the solar system was essentially cleared out, and there have been hardly any impacts in the time since then. The moon has taught us a lot about the formation of the solar system. It has taught us that the solar system was a violent place early on. And in the last 3.8 billion years, there have not been nearly as many collisions as there were in those first 700 million years. It has taught us a lot about the Earth-Moon system. And we will use much of that information about the history of the surface of the moon when we go on to study the history of Mercury, Venus, and Mars, the other terrestrial planets. In our next lecture, we will take a look at the history and the surface of the planet Mercury, very similar to our moon, an airless world covered in craters. I will see you then in the lecture on Mercury.